Okay, let's take a look at an implementation for a set abstract data type in C++. So just as a way of building on some of the previous material we've covered, I could write a very generic abstract base class. And in this generic abstract base class, what I could say is that this set will hold some type of object T. And when I implement this set, I need to implement an insert function, a find function, and a remove. And these are all pure virtual functions, which means someone needs to come along and provide a derived implementation from this class that then fully explains how a set abstract data type works and implements all of these functions. I'm not going to do that directly in this lecture. Instead, I'm going to simplify it so that the syntax is just a little bit cleaner on the slides. And let's just say that we're hard-coded to be integers. So we're going to have an integer set. But I am going to use this abstract base class. So I need an insert function that'll insert an int, a find function that'll find an int, and a remove that'll remove an int from the set. And this is my abstract base class. And now I'm going to extend it to fully implement a set data type. And I'm going to create my implementation based on a linked list. And then after we do that, we'll look at the efficiency of that implementation. Okay, so my derived class will inherit from integer set and will contain a linked list. And for this implementation, I'm going to just include the list from the standard library rather than implementing my own. So I need to do pound include list. And then it is a generic type. And so I need to specify that this is a list on integers. And then I'm just going to give this list the name list inside this object. Okay, and then because I'm inheriting from an abstract base class, I need to implement the virtual functions that are required to make it a concrete class. So I need to implement insert, find, and remove. Okay, so let's take a look at insert. Fundamentally, I'm using a list. So what I'm going to do when I get an item is I'm going to insert it in the list. There's just one trick. Before I do, I need to make sure it's not already in the set. Because if the item's already in the set, I shouldn't insert it again. So what I'm going to do is loop over every item in the list. And this list object has an iterator, kind of like the one we implemented. And I just need to use that iterator to loop over all the items in the set. And then kind of a neat thing about the iterator on the standard list is that you can just dereference it to get the item, to get a reference to the item. So this loop is saying, okay, loop over all the items in the list. And if any of the items equal the item I was passed in that I want to add to the set, then stop and return false. We're not adding this item to the list. Okay, but if I get all the way through this list without ever finding a match, then I'm going to append the item to this list and return true. For remove, I have to do something very similar. I need to loop over all the items in the list. If I find a match, I then erase that item and return true, indicating that I removed something. Else, if I get to the end of this list without removing anything, I return false, indicating I removed nothing. Okay, and then find is a lot like those previous two. I loop over everything in the list and I'll look for the item, and if I find it, I return true, and if I don't find it, I return false. But here, since I'm just trying to find it, I don't need to add or remove anything, right? So it's just looping over the list, looking for this one item to see if it's there. Okay, so that's a pretty simple implementation, right? Using our list and using the operators we know on lists is pretty simple to describe a set. Now, what's the big O of these operations on a set? So if, and let's assume that n equals the number of items that are in the set. So when I do an insert, I have to make sure the key is not present by looping over the whole list and checking for it. And that means I have to visit all n items in the list before I do the insert. But the insert itself, the append, is constant time. So the cost of this insert is really in looking through the list. So this is going to be big O of n, because I have to verify the item's not already in the set. When I do a remove, again, I have to loop through the list, find the item, And that could cost me n steps in the worst case to look through the whole list. And when I actually do the erase, we know that erasing on a linked list is pretty efficient. That should be order 1 time. And so this again is order n. This should be pretty efficient at order n. And a find also requires me to loop through the whole list to look for the item. So that's also going to be order n. So we look up and down this column and we see order n everywhere. Okay, this is really horrendous. This is a very inefficient set implementation. We can easily implement a set using the list, but given that all these operations are taking big O of n time, it turns out this is not a good way to go about it. Okay, so linked lists aren't great for sets. ON is not good. I mean, it's good for some things, but it's not good for a set. The list makes it, basically what it all boils down to is in every single one of those functions, we had to make sure the item wasn't in the list or we had to look for the item in the list. And to do that, we had to look through the whole list. That was the big problem. It's not easy to find something quickly in a list. You have to search the whole list. So that's bad, right? That sequential stepping through the list is bad. And even if it was an array, it would be the same thing. It would still take us a long time. This is brought about, if you think about it, this is brought about by how lists store information, right? They could store an information potentially anywhere in that chain. And so we have to look through the whole chain to find the information. A really good question is, can you do better, right? Can we do better than looking through the long chain of a list? And the answer is absolutely we can. Yes, we can. We can do better using hash tables and we can do better using trees. We're going to look at both of these data structures. Hash tables this week and trees starting next week. Okay, so in summary, we can implement a set in terms of our linked list. The resulting design is inefficient. It takes ON for most operations, which is not good. We can achieve O1 if we do this properly. So we need to look at better ways, and we're going to look next at a hash table.